So in this video, we're going to review exponential functions. Before we get to the functions, maybe let's just start with a quick refresher on some properties of exponents that we should all be familiar with. So we'll use these properties freely in this, so good thing to refresh. So if I take a and I raise it to some power x, and I take a and raise it to some power y, when we multiply these two things together, we add the exponents. If I take a of x, a to the x, and I divide by a to the y, we subtract the exponents. If I take a to the x and raise it to the yth power, this gives me a to the x times y. And if I have two numbers, a and b, and I raise the product of those to the x, it's just the product of ax times bx. So these are some properties we should be familiar with, and we'll need these properties as we kind of develop exponential functions, which you should have seen before. This is really just for review. So let's start with an example to kind of build up our exponential functions. So the population of California So this was 39.2 million in 2023, and it was 39.43 million in 2024. So now we can ask how did the population grow during this time? So we can observe. So often we think of populations of people, animals, whatever, growing exponentially. This only happens for a short time as resources dwindle, but let's go ahead and suppose we're going to do this for this case. So notice if I take the 39.43 and I divide it by the 39.2, this gives me approximately 1.0059. So what this means is population grew, as we can see, because the number is bigger in 2024. And so it grew by about 0.059%. So that's coming from this part here, from 2023 to 2024. So now let's assume the population continues to grow at this rate. So then we can ask ourselves, well, what is the population going to look like each year? So in 2025, it would go up by another 0.59%. So in 2025, the population should be it's the number we had in 2024, which was 39.43, and then it grows by this 59%. We can also write this is 39.2, and we know that this value here is 39.43. That's how we got the 1.0059. And so that's this part goes to here, and then we have this other 1.0059. So overall, this is 39.2 times 1.0059 squared. And we could continue this. So in 2026, the population would be, assuming we continue with the same growth rate, well, we take the one from before this, and if we write down what this is about 39.66 million. Just so we have a number there. So this should then be approximately 39.66 times 1.0059. And notice if we write this in terms of our very first population, we put on another 1.0059. So this is now 0.0059 cubed. And so this is about 39.89 million. And from this we can hopefully see a pattern here. So we have this 39.2, which is our initial population from when we started the measurements. And then we have this exponential factor here that's telling us how we grow. So notice that 2026 is equal to our initial year plus 3. And so we can see this 3 here is exactly what the exponent is that gives us our new rate. So we can then kind of figure out our general formula. So if we want the population, so we can say in general, t years after 2023, right? So t equals 0 corresponds to 2023. The population will be say p of t, which is going to be the 39.2 and then 1.0059 raised to the t. And this is in millions. Okay, so this fits our pattern above. So for example, in 2050, we should have, well, we want to figure out what the t is. So notice that the 2050 is 2023 plus, so I need 27 more years. So this should be my t value. So I want p of 27, which is 39.2, 1.0059 to the 27. And this is about 45.95 million. So assuming the population continues to grow at the same rate, we could then tell the population of California at any time. Now, of course, it's not going to continue to grow at the same rate because eventually there won't be any resources left and things will get too expensive. But this gives us a good approximation for over a short time period. So notice with our function here, we have, when I look at p of t, I can write p of t, I can think of this as p0, which was our initial population. And then I could write this as 1 plus r to the t. Here r is equal to the 0.0059. Okay? And so this term here is referred to as our growth rate. So in general, if r is bigger than 0, this term, the 1 plus r to the t, is going to be something a little bit bigger than 1 raised to the t. So this is going to be an increasing function. This is increasing, and we say we have exponential growth. Okay. On the other hand, if r is less than 0, then notice 1 plus r is really something less than 1. So now the function p is decreasing. So we have p is decreasing. And we say we have exponential decay. So we don't always have to write it as 1 plus r. We could, but we don't have to. So we can also write, and sometimes this will be more convenient, we could just write p is p0 a to the t. So we did this above. So above, my a would be 1.0059. Okay. So now in this case, if a is bigger than 1, this gives exponential growth. And if 0 is less than a is less than 1, we have exponential decay. So we can also graph what this looks like in each case. So let's say this is t, this is y, so let's do two different graphs here. So if we have exponential growth, it's going to look like this. So this is when a is bigger than 1, so this is exponential growth. And this value here when t is equal to 0 is at a height of p0. Now if we have exponential decay, we're going to start up here at our p0, but we're going to decrease, something like this. So this is for exponential decay. So that's what each of those functions would look like. So let's look at some more examples now of exponential growth and decay. So let's start with one with decay. Okay, so suppose an aspirin tablet of 325 milligrams has half-life of 20 minutes. So what does half-life mean? Half-life means that's how long it'll take for half of it to be gone. So in the context of aspirin, this half-life of 20 minutes would be half of the aspirin has already been worked through your system within 20 minutes, which seems like an incredibly fast half-life, but it is actually accurate. That does have that fast of a half-life. So this means, so after 20 minutes, only 325 over 2, which is 162.5 milligrams, remains in the body. So let's find a function that models this. So let's go ahead and say our function is going to look like p of t is equal to p0 a to the t. And we're going to say t is measured in minutes. You could just as easily set this up in terms of hours. And then you'd say the half-life is 1/3 of an hour if you wanted to do it that way. Doesn't really matter as long as you're consistent. So note that we have, if I plug in 0, p of 0 is p0 a to the 0. Anything raised to the 0 power is 1, so this is just p0. And we also know the original amount is 325. So p0 is our 325 milligrams. The other thing we know, well, maybe before we do what else we know, let's rewrite our equation. So just plugging in what we know, this is 325 a to the t. So that gives us a little bit further along on figuring out this equation. So the other thing is we know the half-life. So we know after 20 minutes, 162.5 remains. So in terms of our equation, that means p of 20 should be 162.5. So combining that, I have 1625 is equal to p of 20, which is 325 a raised to the 20. Now if I take the outsides of this equation, look at that part, I want to figure out what a is here. So let's first divide both sides by 325. Now we've seen before above that 162 is half of 325. So this gives me 1/2 is equal to a to the 20. And now I can take both sides and raise them to 1/20. And remember from our exponentiation rules, this becomes a. We multiply these exponents, so this is just a. So using this, I can now write my equation as 325, and then I have my a is 1/2 to the 1/20 raised to the t. And if I want to use my exponentiation rules again, I can combine that t and the 20, so it looks like this. And now we can go ahead, once we have this equation, we can evaluate at any particular time. So after 2 hours, say, so which is 120 minutes, we will have, so we plug in that 120, p of 120 is 325, 1/2 to the 120/20, which is 325 to the 1/2 raised to the 6, which is 325/64, which is about 5.08 milligrams. So we'll still have about 5.08 milligrams in the body after 2 hours. So maybe just write this as a sentence. After 2 hours, it's not a bad idea to get used to writing complete sentences so you actually get used to interpreting what the equations are telling you. So you might have seen before, often exponential functions are written in the form, so p of t is equal to p0 e to the kt, where e is the base of the natural log. So this is approximately 2.71828. So we'll come back to this when we do logarithms. Right now we won't be able to find the k so easily here, so we will come back to this. For now, we're going to stick with our p of t is equal to p0 a to the t. So let's look at one more example here that comes from finance. So let's look at putting money in a bank account. So let's suppose we deposit $100 in a bank account earning an annual percentage rate interest. So this is usually written as APR. Let's say of 4%. So if you have a bank account, you'll be able to see what the annual percentage rate is, and that's what this corresponds to. So this corresponds to getting one interest payment per year. So this is the interest rate if interest was compounded once a year. We'll see in a few minutes how to do this if it's compounded more than once a year, which most likely your bank account is. But let's just go ahead and stick with this once per year thing. So at t equals 0, we would have $100. We haven't gotten any interest yet. After 1 year, we'll have gotten one interest payment, so I'll have that 100, but I'll have gotten interest on it, so 1.04. So this is the 100 plus 0.04 times 100. So notice this is the initial deposit, And this here is our interest on the deposit. Now if I go to t equals 2, I get interest on all of that again. So I'd have everything that I had before, plus I get 4% on it. So I'd have 100.04 squared now, because I'm getting that interest now on everything else as well. So you can think of this is the 100, 1.04. Maybe I'll just leave it like this. Let's just leave it like this for now. We take everything we had in the time before, and notice that 1.04 is telling us keep the amount that we have and add interest to it. So maybe the best way to write it is kind of to illustrate is this is our time from before, and then we do another 4% of interest on that. So we can see if we keep going in this pattern, after t years, we'll have $100, 1.04 to the t. And so this is the amount of money in the account after t years. So now instead of doing this, more likely what your bank account does is it compounds interest once a month. So when we do that, we don't use the APR as our rate anymore. Now our rate for this compounding, so what do? We take the annual percentage rate and we divide it by the number of compoundings per year. So if it's compounded monthly, we get 12 compoundings. So this is our interest rate for compounding once per month. Okay, so let's let m now be equal to the number of months. We'll work with months first, and then we'll change it into years at the end. So if we have 0 months, again, we have the $100. Now after 1 month, we're going to compound this $100. So I'm going to have that $100, but I'm also going to have the interest I get from this. And since now our rate is 0.04 over 12, that's our interest rate. Notice I can think of this as to the first power. If I do 2 months, I take the money I had from the previous month, which is this, and I get interest on that as well. So we can see if we continue this. So after m months, we have 100, 1 plus 0.04 over 12 to the m in the account. So now if we want to compare this and put this into years, so let's change this to years. So notice m months is, if we want to put this in terms of years, so m months is 12t if t is in years. All right, so if I have 12 months, I should get 1 year, so that should correspond to t equals 1. And so on. If I have 36 months, my t here should be 3, which is 3 years. So this allows me to write my equation. If I want to write it in terms of years, I can write it like this. So for example, after 3 years, now you could write the equation in terms of months. That would be perfectly fine. It's just more common to write it in terms of years. So that's why we changed it to years. But you could leave it in months as long as you're consistent. So if we do after 3 years, we have, well, what would our bank account have then? Well, this would be P of 3, so this should be $100 plus 0.04 over 12. Now I plug in the 3 for t, so this gives me to the 36th power. So this is approximately 100 times 1.127, which is about $112.73. So we got $12.73 of interest. So after 3 years, we have earned $12.73 in interest. Okay, so that's our review of exponential functions.